Besides the title slide, I have one slide of content and then one slide that says here's a few practice problems. Again, we're not adding a lot today, we're just tweaking a little bit, but we are introducing you to something that you will be using a lot in the coming months, which is called an ICE table. It's a way to organize the information that you need in order to solve a problem. That's kind of the easiest way to explain it. It's just an organization system. So, here's the one question I'm going to do on the smartboard. I don't know if you need to write this down as much as when I flip over to Smart Notebook and I start handwriting stuff. But here's a question you can be given. Again, let's become comfortable with the fact that you would be given an equation and following it a k value. Although this one has a question mark because you're going to figure out the k value. I believe that was even what I had up on the smartboard as one of our goals today. Recall the k values are temperature dependent. I don't know if that popped up on the web assignment last time or it might pop up today. But again, because endo-exothermic can shift a reaction, that would change the ratio of products to reactants at equilibrium. So that's why it's common to see this value, but you're not actually going to do anything with that number. Okay, second bullet point to the question says a reaction starts between sulfur dioxide gas with a partial pressure of 150 torr. Remember, torr is similar to millimeters of mercury. You do have a conversion on your equation sheet if you need that. I picked this just because I want you to be familiar with different units of pressure. Equilibrium can be done with concentration, or it can be done with pressure. And chlorine gas with a partial pressure of 298 torr. At equilibrium, the partial pressure of the reaction is 13. The reactant is 13 torr. What makes this different is that I'm not just giving you the equilibrium pressures for everything. Because if I did, products over reactants, done. Easy. This is giving you the starting amount of two different things. And it's giving you the ending amount of one thing. I was mentioning before that there's a lab that we're skipping to save time. Actually, this is very similar type setup to what we would do in that lab, where we would know how much reactants we started with, but if you're trying to find the K value, you couldn't figure out the equilibrium concentration just by looking at something. Now, what we did in the lab is we used spectrophotometry to figure out the ending concentration of one thing, and then we did an ICE table to figure it out. So I'm kind of working you through a similar method here. But these two sub-bullet points is what I'm going to cover right now. Calculate the concentration of each species in the reaction at equilibrium. And then once we have that, we can solve for the equilibrium constant K. Good? So, if I start off with the reaction, ICE, initial, change, equilibrium. There are some schools that actually, instead of using an ICE table, they'll use a RICE table. Because you have your reaction, and now what's the initial concentrations that change in equilibrium. Initially, the question said that we had a partial pressure of SO2 of 150 torr. And in a Cl2, we had 298. So in other words, that's what we started with. If they make no mention of the SO2 Cl2, there's none of that. If this is what we started off with, which direction is the reaction going to go to get to equilibrium? Yeah. It's going to go towards the reactants. That means these two things are going to react and make some of this. But here's the problem. We don't know how much they're going to do because it's an equilibrium reaction. And equilibrium reactions only make some of both things. And if you don't know how much it actually will make, we use variables. This, since the reaction is going to be going in this direction anyways, is going to gain a certain amount. Let's call it X. And if this is gaining X, the SO2 must be losing X. The Cl2 must be losing X. Now, some students are concerned about what I just did for the change because they see two X's on the product side but only one X on the reactant side, and they're wondering, how does that add up? These two things combined make one of these, though. Two arms for every one body is a way to look at it. What you would do is, when you're assigning an X, look at the coefficient in front of each thing. If there was a 2 in front of this, which, by the way, changed this formula, but if there was a 2 in front of one of these things, then you would put a 2x. And you'll see practice problems like this over the course of the next couple of class periods when we do this a little bit more. But if we don't know the change, that's how we can figure it out. Now, the one more bit of information that we were given in this problem was we were told at equilibrium, the partial pressure of the reactant was 13 torr. If that's the case, we know what X is, right? 0 plus X equals 13. X must be 13. So now, I can take 150 minus 13. I can get 137. I can take 298 minus 13. 285. This would solve for the partial pressure of each gas at equilibrium. That was the first question that was asked. So the P of SO2Cl2, I mean, if I wanted to make this all official looking and whatnot, P of SO2Cl2 equals 13 torr. P of SO2 equals 137 torr. And P of Cl2 equals 285 torr. So we solve for the equilibrium pressures for everything. And again, the same rules would apply if it was given molarity. Part 2 was solve for the K value. Now this is what I went over last time. We would take K equals products, 137, times 285, divided by reactant, and that would give me a number of, I'm going to not worry too much about sig digs here because it gives me 3003. If I did want to do sig digs, it would be 3.0 times 10 to the third. K is a unitless value. But if you're given equilibrium concentrations right away, products over reactants, done. If you're not given equilibrium concentrations, you want to set up an ICE table to identify, here's what I start with, how much am I losing, how much am I gaining? What we will eventually get into is problems where you're given a little bit of everything to start. Now figure out which direction will you go. That's a topic that we're covering next week. So again, I want to give you one piece at a time to all this mathematical puzzles that we're doing here. Okay, the question said on the bottom in bold, why is temperature staying when this K value is given? If this was an endothermic reaction, for example, we would consider heat as a reactant. If you then increase the temperature, the reaction would shift in this direction to the product side. And if it shifted to the product side, you'd have more products per reactant. Your K value would actually increase in that case. The exact opposite would be said if it was an exothermic reaction. So K values are temperature dependent, which makes it a little unusual. That's why I wanted to bring up that question to wrap this up. What we have